A very good evening, all. Welcome to the problem solving session number 8 of the course Mechanics of Material. So, this week in this session, we will be seeing problems of two categories. Number one is about finding sectional properties. Number two is on solving stresses in a non-homogeneous beam. Okay, so these are the two target or focus for this particular lecture. So let's start first with the section. I'm going to directly start with a problem. So problem number one for the day. Say suppose we have a section, a channel section. Let me draw it a little neatly. Given the section is given and we need to find the centroid and the moment of inertia. Okay, so let me quickly write the dimension. So this is 500, this is 20, this is again 20, and the thickness everywhere is 20. The bottom dimensions are say 300, and the total uh, depth is say 700. Okay, fine. So right, we need to find the values, various values of the coordinates. By the way, my coordinate system is here. This is my z coordinate system. This is my y coordinate system. My origin is here. Okay, right. What we have to find for this question, we need to find a what is centroid coordinates, that is x, not x, y and z. So y centroid and z centroid is what? And b, we need to find moment of inertia I about z axis and about y axis and about zy axis or yz axis, product moment of inertia, right? So five questions we need to solve, right? So let me start with the centroid. How will we find centroid? In general, centroid can be found using the product, taking the moment of individual areas and equating with the moment of the entire area. So I'll like to write the centroid formula. The centroid coordinate for yc is given by integral of the area, like moment of the area d of a y times d of ax divided by the total area, right? So this is centered coordinate for y, and similarly for that c, z times dAx divided by integral dAx, right? Fine. So this is just coming from the moment of area of individual cross section. Now this actually tells us a1 y1 plus a2 y2 plus we have how many sections here? One, two. I'm going to consider this as one section. and this as one section. So 1, 2, 3, 4. We have four sections. So A3 Y3 plus A4 Y4 divided by A1 plus A2 plus A3 plus A4. Okay. So now individually, quickly let's write what are the section and what are the uh, properties. So this is section 1. This is section 2, and there is a section 3. Yeah, what are the dimension of section 1? Dimension of section 1 are 520, and here for section 2 it's 700 minus 20, which is 680, and this way it is 20. For section 3 it is, it starts from here 300 minus 20, which is 280, and the thickness is 20, right? And what for section 4? So small section 20, and oh, there we need to give, I didn't note it down. So this total is 100. So that will be 80, na? Yeah. This way it is 80. So let me draw it little longer. The section 4 is this 80, and this is 20. 1, 2, 3, and 4. Now properties, what is A1? A1 is directly we can compute. 500 into 20 will be 1000 mm square. What is Y1? Y1 is from the origin. What is the centroid of section 1? So from the origin, centroid is 700 minus 10, 20 by 2, just 10, which is 690 above. Okay, plus 690. What is Z1? Similarly, the from the origin, z-axis, my Z1 will be minus of 250, correct? 500 by 2. Now what is A2? A2 is 68 times 2. 60 times 2 is 120, 8 times 2 is 16, so 136, 0, 0, right? And what is Y2? Y2 is, yeah, it's straightforward. Half of 680, which is 340. What is Z2? Again, it is straightforward, minus 10. Okay, 20 by 2. It is closer to the touching the origin. So that's why it is straightforward. Now, what is A3? A3 is 280 times 20, which is 28 twos are 56, 5600. What is Y3? Straightforward 10. And what is Z3? Z3 is from here it is 20 plus 280 by 2, right? Minus 20 minus 280 by 2, which is minus 20 minus 140, which is minus 160. Am I right? Yeah, fine. Good. So finally, what is A4? 80 times 20, which is it is 1600. What is y3? Y3 is 20 plus 40, so 60. What is Z3? Z3 will be 300, negative of 300, and minus this 10. So 300 minus 20 by 2. This is negative of this. So it is negative 290. Okay, I hope all the values are right. Now let's put everything into the centroid. So YC formula centroid is equal to, directly let me substitute one by one. A1, let's use a calculator. A1, Y1, 690, plus A2, 13,600 times Y2 is 340 plus 5,600 times Y3 is 10 plus 1,600. Oh, oh, I made a mistake. Sorry, okay, 16 minus 16 is nothing, plus 1,600 times Y3 is 6. Sorry, it's Y4. No, why I am writing here Y3. Y4 Z4. Y4 is 60 times 60. Okay, this divided by the A1 plus A2 plus A3 plus A4. What is A1 plus A2 plus A3? 1000 plus 13,100 will give us. Oh, by the way, for 520 size 10,000, right? Hmm. Right. Yeah. So I think above itself we have to change. So 10,000 times 690 plus 13,600 times 340 plus 5600 times 10 plus 1,600 times, again I'm making this mistake, plus 1,600 times 60 divided by A1 plus A2 plus A3 plus A4. 10,000 plus 13,600 plus 5,600 plus 1,600. So let me note down area total equal to 30,800 mm square, and YC will be everything divided by this will giving me 379.09 mm. Okay, so this is above the Z-axis. So YC is done. Now what is ZC? ZC will be, again I have to multiply everything. Let's do A1 10,000 times 250. It's negative 250, but just I'm keeping in my mind, plus, oh wait a minute, 10,000 times 250 plus A2 is 13,600 times 10 plus A3 is 5,600 times 160 plus this is A4 is 6400 1600 times 290. Fine. Yeah, this is the value divided by A1 plus A2 plus A3 was 30,800. So I'm getting 129.74 mm. Right? Okay, so right. That's also done. Next, moment of inertia. IZZ first. So how will we find? We'll use something called parallel axis theorem. So when a centroid of the cross section is away from the net centroid, the entire centroid, if it is shifted by a distance d, so its moment of inertia about the original centroid will be equal to its local centroid moment of inertia plus area of that cross section times the distance square. Okay, that's parallel axis theorem, no? So we'll use that for finding. So IZZ will be given by IZZ of 1 plus IZZ of 2 plus IZZ of 3 plus IZZ of 4. Okay, so this is equal to what is IZZ 1? 500 into 20 cube by 12. BD cube by 12. 500 into 20 cube by 12 plus 500 times 20 is the area of the first section. And what is the distance between its centroid and the entire centroid? First section is at 690 and the entire centroid is 379.09. So 670 minus 379.09 the whole square. Okay, this is IZZ1. Similarly, plus what is IZZ2? IZZ2 is 20 into 680 cube by 12. 20 into 680 cube by 12 plus area into distance between the square of the axis. So 340 minus 379.1. 340 minus 379.09. The whole square. Plus IZZ3 will be 280 times 20 cube by 12. 280 times 20 cube by 12 plus 280 times 20 times square of the distance between them is that uh, here this is 10 and yeah 10 and 379 plus finally the section 4 which is 20 into 80 cube by 12. 20 into 80 times square of distance between them. Y4 is 60 and YC 379 per 9. 60. 60 minus 379.09 the whole square. Now adding everything, we are going to get the moment of inertia above y axis, the z axis. Okay. Now let me uh, maybe I'll finish it off. So I have a big expression to solve here, to put in calculator. So 670 minus 379.09 to the whole square times 10,000 plus, let me be very careful, 500 into 20 cube by 12 plus 20 into 680 cube by 12 plus 20 into 680 into 340, 50, 60, 70, 39.09, 39.09, the whole square. Okay. Plus again 280 into 20 cube by 12 plus 280 into 2, 5600 times 369.09, the whole square. 369.09 to the whole square. Okay, this plus last term 20 into 80 cube by 12 plus 20 into 80 into 60 minus 379.09, the whole square. Okay, finally we got an answer. Okay, so this is equal to 2.318 into 10 to the power 1, 2, 3, 4, 5, 6, 7, 8, 9, 9 mm per 4. Okay, that's it. So this is IZZ. Similarly, you can find IYY. Now I'll do a calculation for IZY. IZY. IZY equal to same way, we have I say YZ, YZ1 plus I YZ2 plus I YZ3. Now what is I YZ1? IYZ1 is equal to area, because actually IYZ about CG plus area of 1 times that y minus y naught times z minus z naught, right? So any of this is going to be 0. Product moment of inertia about the centroidal axis for a symmetric section is going to be 0. So what will remain? Only a times y minus y naught times z minus z naught. So this is equal to, area is, a1 is 10,000 times y minus so y1 minus y naught. What is y1? 200, 690. 690 minus Y naught was 379.09. 379.09 times what is Z? Z? Z1 minus 250, and this is also negative, right? Minus 250 minus 129.74 minus 250 minus of minus 129.74. Okay, fine. So yeah, this will give us the value of IYZ1, so which is 690 minus 379.09 times 10,000 plus, not plus, it's into minus 250 minus plus 129.74. So this will be 1, 2, 3, 4, 5, 6, 7, 8. So minus 3.739 into 10 to the power 8, right? Power 4 into 3, 4, 5, 6, 7, 8. Now, what is IYZ2? Again, A2 into Y1 y2 minus y naught times z2 minus z naught. So this will be equal to a2 is 680 into 20, 680 into 20 times what is y2? 340 and 379. 340 minus 379.09 times z2 is minus 10 minus of minus 129.74 minus 10 minus of minus 129.74. Okay, so this will give us 340 minus 79, 39.09 times 20 times 680 times this will become 119, right? 119.74. So this will be 6.36123456 7. So since I am writing 10 power 8, this into 10 to the power minus 8, when I do, I'm getting 0.6366 into 10 to the power 8. Okay, and what is y z3? A3 into y3 minus y naught and z3 minus z naught. If anyone solving listening, better that we you write parallelly so that you can able to get any mistake if I made here. So A3 will be 5,600 times y3 minus y naught 10 minus this thing will be 300 and negative 369.09. Z3 minus Z naught will be Z3 is minus 160 minus or minus plus. So minus 160 plus 129.74. This will be 129.74 minus 160 times 369.09 times 5600. This also let me write in terms of 10 power into 10 power minus 8. So I'm getting minus 0.6254. All are very less except one, yeah, 8 power 4. Finally, for that small fourth section, we can get a IYZ4. IYZ4 will be equal to, yeah, same way, A4 into Y4 minus Y naught times Z4 minus Z0. So A4 is what? A4 is 1600 times Y4 minus Y naught. Y4 is 60 minus 379.09. 60 minus 379.09 into Z4 minus Z0. Z4 is minus 290 minus of minus, so this will be a negative in whole. Minus 290 plus what is that? Z0 plus 129.74. Okay, so this will be 60 minus 379.09 times 1600 times 129.74 minus 290. Okay, so this into 10 to the power minus 8 will give us 0.8182 per 4. So totally YZ will be the addition of first, second, third, and fourth. Right. So this minus 0.6254 minus 0.6366 minus 3.7. Important equations. So the topic is stresses and deflections in inhomogeneous beam. Okay. So in in the case of homogeneous beam, we already have the bending equation, that is minus sigma xx by y minus y naught is equal to mg by izz equal to e into d square delta y by dx square. So this is the equation. Now, suppose if I have different materials, what will be the difference? Of course, E in this case, it is a constant, whereas when the materials are different, the Young's modulus of each of the material is going to vary, and hence there will be a difference in the equation. Now, I'll just highlight some of the important equations. So displacement field will be the same, minus y naught times d delta y by dx times ex plus delta y of x ey. Right, the displacement field. The strain will be almost the same. Epsilon xx will be displacement free. From that, we'll find the strain, which is minus y naught d square delta y by dx square, and we can also find this stress, right, using the constitutive relation, right? So y minus y naught d square delta y by dx square. Okay, so I'm using the other part of the equation, and I'm keeping e as e of y, right, in this bending equation. So the minus in this minus will get cancelled. Fine. So here the force equilibrium and the moment equilibrium will give us the force equilibrium is sigma xx dAx is the net force will be equal to 0, and the moment equilibrium will give us sigma xx y minus y naught dAx equal to moment applied, right? So mg. Now this, when we expand, like when we substitute the expression for sigma xx, so it will become e of y minus y naught d square delta y by dx square dAx equal to 0. So this implies, since x is dy by dx is a function of x and it is constant in the case of y and z integral, so it can be taken out, and hence we can find an expression for y naught from this, right? Y naught is the important expression that we are looking for, equal to integral ax e of y dAx divided by integral ax e of y dAx. Right, so that's it. Okay. So similarly, when we when we use the moment equation, the other equation, so that implies uh, integral. See, instead of sigma xx, we can substitute e of y. Y minus y naught is there already, so there will be 2y minus y naught the whole square d square delta y by dx square dAx equal to mg. Now this implies the d square delta y by dx square is equal to mg by integral of e of y to y minus y naught the whole square dAx. Right. So when we write it combined, d square y by dx square equal to emg by e of y into y. Similarly, this is equal to sigma xx divided by that e will come down. So the modified bending equation was, what color we can use? Yeah, red. Modified bending equation is minus sigma xx by e of y into y minus y naught is equal to d square delta y by dx square equal to mg divided by integral e of y minus y naught the whole square dAx. This is AX. Okay, so this is the modified bending equation that we can use for non-homogeneous beam, right? If E is not a constant. Now, in this, the two equation that is y naught y naught and this integral of e of y into y minus y naught the whole square. So these two are what actually we need to focus a little. So maybe I think we'll solve using an example directly and see what happens. Okay, let me just take the problem. Yeah, I got it. So problem number two. Okay, so we have got the expression for the bending equation in a non-homogeneous beam, and it's like this. So now I just want to add one more thing here. Suppose if we have a problem of non-homogeneous beam, the same can be solved in another method also, without invoking integration stuff like that. We can you simply convert the problem into a linear or a homogeneous problem and then solve using the normal bending equation, right? So that is the method of modular method of using modular ratio. Okay, so if you want to understand more, you can watch the lectures, weekly lectures. So like if you are using this integration in computing the centroid or in computing the moment of inertia of cross section, what you will get is like you will get like same expression, but what happened is that suppose if I have non-homogeneous material, say here material 1 and material 2, and this I can convert into an equivalent material such that my material 2 width alone has increased. The width of my this material, say this this increase. Say suppose if this is B and say this is small d and this is the E. Now my material 1 Young's modulus, say it is E1 and material 2 is E2. Now I define M, which is called modular ratio, as E2 by E1, right? And I just multiply this with MB. Okay, so this we call as transform section. So this will be equivalent section. Okay, now it is of the same material. All are material 1, right? So now we can solve this section using the same the old bending formula, that is the minus sigma xx by y minus y naught equal to mg by izz equal, right, this equation e into d square y by dx square. Okay, this e won't come here, right? E won't come. Fine. By the e by r. Sorry for the interruption here. Okay, so this is the bending equation, but here E was constant, right? So E will just come just like that without any variation. Okay, this is the one which we have already seen, that is for homogeneous beam, homogeneous section, right? Fine. So this is a simplest method, but yeah, we can do by any of the method. Let's take an example problem and see how to solve. So in the example problem, we have been given with a question, problem number 2 for the day. So we need to find. We have been given with a simply supported beam, 8 meter long, is carrying a concentrated load at midspan of load values 20 kilonewton. Okay, the position is at midspan. Right now, the cross section of the beam is given like this. This is a cross section given there is a wood here and another material, there is steel here. Okay, this is wood region and this is steel region. Fine. Now we have been given with the width of the section as 25 centimeter and the total height as 30 centimeter and the thickness of the steel portion as 5 centimeter. Okay. Right now, what we need to find is that we need to find what are the stresses, maximum value of stresses induced in both the materials. That is, what is the value of, say, compressive stress in wood material equal to what? And what is the value of tensile stress in the wood material equal to what? And what is the value of tensile stress in the steel maximum value? Okay, all these are maximum value they are asking. And also we need to find the shear stresses, maximum value of shear stress in the wood and maximum value of shear stress at interface of both steel and wood. Okay, so totally there are 5 questions. Now let's proceed like how to do. First, we need to find the for finding stress. Like we can use this formula, yeah, of course, but we need to convert them into homogeneous cross section. So how to convert? First, we need to find what is the modular ratio. By the way, Young's modulus of wood is given as 10 gigapascal. Young's modulus of steel is given as, mm, sorry, it is 20 and this is 200. Okay, so these values are given. And yeah, let's first convert them. So what is the modular ratio that we get? The modular ratio here is the ratio of steel, Young's modulus of steel to the Young's modulus of wood. This is equal to 200 by 20, which is equal to 10. Okay, so this is the value of M. Now, when we convert this section, we'll get this Okay, let me draw a little neatly. Okay, so this is the converted section. This is step number one. First, we convert the section into an equivalent transform section. So the width above is 25. So I am writing in terms of mm. So 250 mm. So the width below will be m times 250. This is equal to 2500. Okay. Now the total height is 300, and this is 550. Okay. So now first step, we need to find the centroid. Only then we can able to find the moment of inertia, and then we can able to calculate the stresses. Okay. If you want to use this formula, we know mz, yeah, because load is given, we can find mz easily, but we need y naught and we need izz. Okay. We'll go one by one. First, finding the centroid of the cross section. Finding centroid. Okay. So let's fix the origin somewhere here at the bottom. Say this is my y-axis and this is my z-axis. Okay. Uh, Typically, it is good to take z-axis in the other way, since the longitudinal axis is x-axis, which is along the beam. So this is y and this is, say, z. Okay, so this is my origin O. Now, how to find centroid? There are two areas. So directly I'll write y coordinate of the centroid. Y bar will be, first assume this is my first area. Okay, first area is this, and second area is this. So for the first area, it is 250. It is 250. And second area, this is 50, but this is 2500. And what is y1 for the first area? Y1 is equal to 300 by 2, sorry, not 300 by 2, 250 by 2 plus 50, right? So y1 will be 250 by 2 plus 50 will be equal to 125 plus 50, 175. y2 will be y2 will be 50 by 2, which is 25. Okay, 25 mm. What is z1? Z2? Z1 will be minus, the total is 2500, so minus 250, half of 250, so 2500 minus 250 will be 2250, and half of that will be 2250 by 2 will be 1125. Okay, it is z1 will be, from here it is minus 1125 plus, again there is 250 rectangle, so 250 by 2 is 125. So this will be minus 1250. Okay, similarly Z2 will be minus 1 2 minus 1250. Okay, so Z1 Z2 over. Now what is centroid? Y bar will be that we have that integration, right? Integral uh, y dA divided by integral dA, right? Of ax. Now this will be equal to a1 y1 for the current thing, a1 y1 plus a2 y2 by a1 plus a2. So this will be equal to 250 times 250. Y1 is 175 plus A2 is 2500 into 50 times Y2 is 25 divided by 250 square plus 2500 into 50. Okay, total area. So this will give us, let's use the calculator. 250 times 250 times 175 plus 250 times 500. 250 times 250 times 500 divided by 250 square plus 2500 times 50. This 225 mm. Okay. So y bar that we are getting is 225 mm. 225 looks too high. Maybe if we done correctly. Just let me check it one more times. 250. If I want to do it other way, like 250 cancel. Here 25 0 cancel. Here again this will become 10 and 250 will get cancelled. So remaining will be 250 times 175 plus 250 times 2500 times 5 divided by 250 plus 500, which is 750. 75. Okay, there is an error in this. So this 75. In the initial calculation, there was an error. 250 square into, I guess there was a mistake in the bracket which I used, into 2500 into 50 into 25, the whole divided by 2, right? Oh, by 1, the whole divided by, I want one more bracket for safe. So 250 square plus 2500 into 50. Yeah, 74. Okay. Initially, I have done some bracket mistake. So 75 mm from the bottom, okay, from the y-axis. Similarly, for z, we'll get almost the same. Z equal to a1 z1 plus, this should be symmetrical, but still let's do a1 z1 a2 z2 by a1 plus a2. So this is equal to 250 into 250 times z1. Z1 will be minus 1250 minus 1250 plus A2 2500 times 50. Z2 will be again minus 1250, the whole divided by 250 times 250 plus 2500 times 50. So this will reduce to 1250, and here it will become 10. Now here also it will become 10. So remaining thing will be minus 250 times 1250, 250 times 1250, then minus 1250 times 500, 1250 times 500, divided by 250 plus 500 is 750. So yeah, of course, it's symmetric section. So I'm getting the half of the total value. Okay. So now x, y bar, comma, z bar is 75, comma, minus 1250, or y naught, comma, z naught. Push. Y naught, comma, z naught is given as 75, comma, minus 1250. Done. Centroid is done. Next, let's calculate the moment of inertia. Moment of inertia of this transform cross section. Finding moment of inertia. So IZZ, we have to find moment of inertia about the ZZ axis. Now again, we use parallel axis theorem. So IZZ, there are two sections. So IZZ will be IZZ1 plus IZZ of 2. Now IZZ of 1 will be given by 250 into 250 cube BD cube, 250 into 250 cube by 12 plus 250 times 250, the area, into square of distance between them. Square of distance between y1 minus y0. Y1 is 175 minus 75, which is 100, plus I z2 z2. Z2 z2 will be 2500 into 50 cube into 50 cube by 12 plus 2500 into 50 into square of distance between the thing. So here 75, that is 25, right, 25, 25, 25 minus 75, the whole square. So this is moment of inertia of cross section, which is given us 250 power 4 by 12 plus 250 into 250 into 100 square plus 2500 into 50 cube by 12 plus 2500 into 50 cube by 12. 2500 into 50 cube by 12 plus 2500 into 50 into 2500 into 50 into 75 minus 25 is 50 again, 50 square, which is 2500. 50 into 50. Okay, so we are getting 1.28 9 into 10 to the power 9 mm per 4. Okay, so this is moment of inertia about ZZ axis. Okay, from the about the cross section, centroid of the cross section. Now, what is the next thing? Finally, we need to find the stresses. So let's just go ahead. Sigma, finding stresses. So how to find stress? That is sigma equal to sigma xx m by y equal to m by I. This is equal to sigma xx is here is y minus y naught mz into y minus y naught by iz. So now what is mz? Mz is the bending moment about z axis which is acted due to the load acting in the beam. So mz will be a separate subcomponent. So mz will be, what is the load applied? Simply supported beam 8-meter span. So simply supported beam with the point load at the center. So it will be PL by 4. So what is P? P is 20 kilonewton. L is 8 meters. So 20 into 10 power 3 into 8 by 4, which is 8 is again meters. So let me write in terms of mm. So this will be 40 into 10 power 6. Newton mm. Okay. So everything we can substitute in the equation of sigma xx. in order to compute the stresses. So only thing which will vary is the length of, not length, the vertical distance of the fibers. Yeah. So let's proceed. So for first question we need to find is what stress, sigma compression in the wood. So this will be sigma equal to m, here it is m into y. There is a negative sign here. So substitute everything. Now for wood, y is equal to what? For compression in the wood, y will be, it will be the top layer. So the maximum will be at the top layer. So what it will be the length, distance of the top layer from the origin? It is 300. Okay. So this will be sigma equal to minus mz is, just now we computed 40 into 10 to the power 6 into y minus y naught divided by Iz. Y, what is y? This is 1.289 10 power 9. Y is 300 minus 75. This gives us the compressive stress. Okay. So y equal to 300. So sigma equal to minus my by I just substitute the values. So all are in Newton mm, so we'll get in Newton per mm square. So this gives us, yeah, 40 into 10 to the power 6 into 300 minus 75, which is 225 divided by 1.289 into 10 to the power 9. Okay, this is a negative. So minus 6.982 megapascal or Newton per mm square. Okay, and this is compression. Next question: what is the tensile sigma tensile in tension in the wood equal to what? Now again, sigma will be equal to my by I. So at wood, the tension will occur at which fiber? This fiber at the interface. So it will be a 50, right? So y will be equal to 50 mm. So this implies, let's substitute sigma will be minus 40 into 10 to the power 6 into y minus y naught 50 minus 75 divided by 1.289 into 10 to the power 9. So this implies uh, we'll get this 10 power 10 power 3 for minus 40 into, so minus or minus will become plus 40 into 25 will be 1000. 40 into 25 divided by 1289, right? 1289 will be 0.776 megapascal. Okay, that's it. Next, what is the tensile stress developed in steel? Okay, now this will be for steel, my Y will be 0, right? Y is 0 because the maximum value of the stress will be at the extreme fiber, so it will be 0. So this implies sigma equal to minus 40 into 10 to the power 6 into 0 minus 75 divided by 1.289 to 10 power 9. So this will become 10 power 3. This is equal to minus into minus plus again. So 40 into 75. 40 into 75 divided by 1289, which is 2.327 megapascal. Okay, now actually this is the stress induced in directly. Now, if you are using this modular ratio concept, for the case of stress alone, like we need to multiply by the modular ratio. That is, the stress profile will be like that, like this. Now, the strain profile is linear, okay, irrespective of both the materials, whereas the stress profile will be like this till the material 1. In the case of material 2, what will happen? It will be like this. Like if I want to convert into direct case, uniform material case, so this will be m times whatever it is, that much level of magnitude. Okay. Now m is 10, so if I want sigma st tension is 23.27 megapascal. Okay, so here this alone we have to make a note. Like if you want to find the stress for the another material. Next question is the shear stress. Shear stress at the interface. Maximum shear stress at the interface. Interface between steel and wood. Right. How to find? No, shear stress formula that we know is tau is equal to VQ by I V, right? Now V is nothing but the maximum value, V max, of course, because we want tau max, so it is V max. What is V max for this case? It's a simply supported beam with a concentrated load at center. So this will maximum shear is going to be half of that. So half of that, right? This is V max will be maximum. The load applied is 20 kilonewton. So half of 20 into 10 power 3, which is 10 power 4 Newton. Right? What is Q? Q is this ICC. Okay, Q is the area moment of the moment of area from the section where we want to find the shear stress. So in this case, we have something like okay, we have something like this, right? And we want to find at the interface. Now this is going to be, this is 250 and this is 250 again. Q will be area moment of inertia. This centroid will be somewhere here. This centroid will be somewhere here, and the neutral axis of the cross section will be somewhere here. Say now this A into y bar. Now this y bar is the distance between this centroid and this neutral axis. This and this is y bar. So this will be equal to Q will be equal to area of that is 250 times 250 times y bar. Y bar will be this centroid is 250 by 2 plus what is this 50 na 50 minus y naught. Y naught is 75, correct? So this will be, the Q value will be in mm cube. So 250 square times 125 plus 50 will be 175, minus 75 is 100. 6.25 into 10 to the power 1, 2, 3, 4, 5, 6 mm cube. This is cube. Okay. We are ready to substitute. What is B? B is this length, which is 250. The width of the section at the interface, it is 250. Now tau max tau will be 10 power 4 into 6.25 into 10 power 6 by I was 1.289 into 10 power 9, 1.289 into 10 power 9, B was 250. So this will be 10 power 6, 10 power 4 will be 10 power 10, 10 power 9. So there will be one more 10 above. So 62.5 divided by 62.5 divided by 250 into 1.289. Excuse me, 0.194 megapascal. So tau. Okay, that's it. Now maximum value, the overall or maximum value at the neutral axis will be last question. Maximum value at neutral axis location. At neutral axis location, if you want to find, then again tau equal to VQ by IEB is Vy is Z. Now Q will differ because we need to find at the neutral axis. Vy is same, IZZ is same, and where is the neutral axis? Yeah, it is at 75 mm above, right? So B is same, but Q will differ. So Q, how to find Q now for this? So Q, my neutral axis is at somewhere here, say, and I want to find this area moment of this area. Say the centroid is somewhere here. Now this will give rise to, from here to here it was 75. So total above it will be 225. So this will be 112.5. So my Q will be this area 250 times 225 times 112.5. Okay. So 250 times 225 times 112.5, which is 6328125 mm cube. Now this will will substitute back. So it was 20 kilonewton, which is 10 kilonewton, 10 power 4 into 6328125 divided by I is 1.289 into 10 power 9, 1.289 into 10 to the power 9. B is 250. So this 10 power 4, 10 power 5, it will become just divided by 1.289 into 250 into 10 power 5. 250 into 10 to the power 5. So this gives us 1.196 megapascal. Okay, so it is higher than that. Fine. So that's it. Okay. Now, actually, maybe suppose if you want to design, say, suppose in the same problem, we have fixed a nail. Here there is, assume here we have a nail between the steel and the wood. In this interface, we are fixing some nail. Okay. This is at the cross section. So here we will, it will be visible like this. And in the longitudinal section, say I am cutting some section, the longitudinal section, we will have the same here, here, here. We don't know the spacing. Now, what is the task given to us? We need to find the spacing and we need to design this. Okay, the diameter, maybe the diameter of the nail, the spacing of the nail, and say suppose we want to take allowable load. Allowable load is given in the problem. allowable load is 10 kilonewton, say. What will be the spacing uh, recommended equal to what? Okay, safe spacing will be what? Now how to find this, right? So same way we'll find the shear stress at the interface between the steel and the wood, which we already have for this problem. That multiply by stress times the area. What is the area? This influence of this will be S times width will be B. Okay, this is the total load allowable. Fine. F nail allowable of shear. Okay, right. So this is equal to, already we have 0.194 0.194 into S times 250 equal to 10 into 10 power 3. This will give us S equal to 10 power 4 divided by 250 into 0.194. So 206.18. Okay.